My name is Gregory Antell, and I'm a product manager, machine learning architect at BigML. So our mission at BigML is to make machine learning very consumable and accessible to people of all different backgrounds with regard to machine learning. So interpretability of machine learning is really central to every new feature that we provide. Additionally, our team being distributed, it's about 65% located in the EU, and looking through the data yesterday, at least 15% of our users are also based in the EU, but probably much higher. And just full disclosure before we get started, I'm definitely not a lawyer, and none of this should be construed as, or misconstrued as legal advice. So I just want to get that out of the way as well. So I've already mentioned GDPR a few times about defining it. What it stands for is the General Data Protection Regulation, and we are in the GDPR era as of May 25th of this year. That's when the directive went live. It was called a Copernican revolution in European data protection law as much as 6 years prior to actually being the official law of the land. So this has been being generated for quite a long bit of time. And there's three major shifts of what GDPR is relative to a former EU directive on the same topic that was rather toothless in nature. So the first one is that GDPR is not just a suggestion, it's now a real law and should be regarded seriously. It can levy fairly severe financial penalties to violators. So the maximum fine is 20 million euro or 4% of global revenue, whichever is greater. So that can be well into the billions for very, very large tech companies potentially. And it's global in scope. So just because you're in the United States right now, it doesn't mean that this does not apply to you. It's not something that's levied only to EU companies. It refers to the management of anyone from the EU subjects data. So this is 500 million people. I mean, and they're not all living in Europe all the time. So if they're in the United States and you have their data or you're doing business in Europe, this can apply to you. So I'd like to summarize the broader GDPR debate and limit the total number of characters by going to Twitter. And so there was a fairly controversial tweet by Pedro Dominguez earlier this year in January, so a few months before GDPR launched, stating that starting on May 25th, the European Union will require algorithms to explain their output, making deep learning illegal. So the knee-jerk reaction might be, to say that this is too extreme, we're going too far, what's wrong with deep learning? It's very applicable to lots of situations, it's solving lots of problems. But it did stir some productive conversation here regarding how do we actually deal with GDPR. So there's some philosophical responses to this tweet. So for example, there's this response that said, well, that makes human intelligence, which is also unexplainable, illegal by inference. So it's a very philosophical argument, and we're not going to get into this today, hopefully. What I really want to focus on is the pragmatic solutions to GDPR and how do you actually deal with the reality of this law. So Louis actually responded to this tweet saying, what does an output explanation look like? And Tom Dietrich, another machine learning researcher and a co-founder of BigML, he said, don't you think such methods such as LIME could give acceptable explanations or saliency methods for images? So I'll touch a little bit on LIME towards the end here and what that means. And so that will be the focus of this talk, really. So the main aspect of GDPR with regards to machine learning has to deal with this idea of the right to explainability, which was addressed in the tweet. So GDPR is very broad overall in its overall scope. It applies to how you manage data and various aspects of privacy. So it's not an entire directive focused on machine learning. The parts that really refer to machine learning are two different sort of articles or subsections. But one is in this section, Articles 13 through 15, which states that data subjects have a right to meaningful information about the logic involved, as well as the significance of the consequences of automated decisions. So, pretty wishy-washy or broad language overall. But what gets more commonly cited is Article 22 and also this part of the directive called Recital 71. And what I learned recently is recitals aren't actually part of the directive officially, but they're sort of intended to provide the context of how it should be applied or regulators are likely to apply it in the future. What this recital states is that data subjects are entitled to an explanation of automated decisions after they're made, and they have the right to challenge the decision. So what we really care about with regard to the explainability is basically consent of the user, like informing them enough so that they know whether or not they want their algorithm to be applied, because they now have the right to object to like opting into algorithmic decisions or machine learning decisions. So why do we care so much about explanations, or why do these regulators care about explanations? So you can imagine that, you know, if you were to be subject to a job application sort of algorithm and you got a rejection, there's lots of questions that might come to mind about, you know, why does this work? Like, why is this decision fair? Like, what would change the answer? And, you know, I've definitely received a job application rejection within about 30 seconds and immediately was like, what was wrong with, you know, my resume? They did nothing. Well, anyway. So, I mean, the idea here is that you can ensure fair, consistent, and ethical models. So, you know, the gamut of explanations of machine learning interpretability can vary from, you know, being a very powerful engineering tool to understand the internal mechanics of your model, but there's also this idea of essentially accountability to society as well. So explanations, you know, open up black box models, as were referred to a lot in the previous presentation as well, you know, to ensure consistency. And by doing this, you also can increase the trust in algorithmic decision making. So you can imagine now, like the bar for like how much trust there is in an algorithm might really shift over time, as long as you're able to provide reliable explanations along the way. And finally, even if you disagree with all these things, the reality is you need to be compliant with government regulations now under GDPR. So what we really need here is human-friendly explanations when we think about this, because a human is the end consumer of a machine learning explanation. And so explanations should obviously be truthful, but a full accounting of the entire truth is really overkill and becomes less intuitive. So if you give back every single weight in your giant neural network, sure, you can figure out, I guess, how that pixel eventually maps to some classifier. But, you know, it's not really interpretable at all, and that's not what's meant by machine learning explanations. Because you have to remember the fundamental goal here is to inform people so that they can opt in or opt out of their decisions being subject to an algorithmic decision. So there's some major principles with regards to human-friendly explanations that can be applied when you're thinking about how to best explain a machine learning model. One of them is that humans like contrastive explanations. So they don't care so much about why is their credit score 650, but they care why is theirs 650 and someone else's 826, and what they can do to change their credit score, for example. So there's some limitations to this. Of course, it sort of like requires a reference to compare against and so forth. But if you're able to introduce some sort of contrastive or exploration aspect to machine learning exploration, it's to your advantage. Another aspect is, and I kind of referred to this already, is selectiveness, or essentially that explanations should be short. 1 to 3 of the most important reasons are important. Humans intuitively understand that the world is very complicated and there can be a lot of factors that contribute. So even if things are more complex in reality, it's still, you know, generally best practice in relating your explanation to a human end user to keep an explanation concise and give the, you know, the most important reasons, or the most 1 or 3 reasons. So if you imagine like an algorithm that is determining whether or not a patient has the flu, that's a very, very complicated process. You know, you first have like an assessment of the symptoms that present, but if you really want to get into the causal nature of it, you have the whole physiology of disease, how that develops, and you can go into the molecular biology level, and it's, you know, turtles all the way down eventually. But what we really care about is like what are the most important contributors for making that decision, and how did the algorithm come to those? And finally, explanations are social. It's a communication between an explainer and an explainee, and so it should be consumable by somebody who is typically non-technical, especially, you know, if you're developing an algorithm to apply some sort of automated decision making for, you know, the general public. So ideally, you provide these things in plain language. So giving back a bunch of linear algebra is not really the solution. That's not what is meant by an explanation. Another frequently asked question about GDPR is, does it ban deep learning? So just going back to this tweet by Pedro Dominguez, it's telling that you use the language deep learning here and not machine learning, because what he's really referring to here is this inherent trade-off that you often see between interpretability and performance of algorithms. So there's a dozen different versions of this sort of plot you can find online, and they're all sort of made up because there's no units for really either of these axes if you really get down to it. But in general, I'd say, like, most people agree that this holds true, that neural networks in general can generate the most cutting edge performance, but they're less interpretable. Is deep learning banned by GDPR? Well, I guess it really depends on if we can consider them explainable or not, because that's really what we care about. So I just want to give a little bit of context before getting into the details a little bit more here. There's a little bit of jargon with regards to machine learning interpretability, since there's lots of flavors. And one of the biggest, I guess, areas of interpretability is this distinction between global interpretability and local interpretability. So this is just a very, very small, simulated data set of a patient, and we're trying to determine whether or not they have diabetes or not. So, this column on the far right is and this data is the same between the two. What I really want to contrast here is that global interpretability determines whether or not these features, such as glucose, blood pressure, age, how much they're contributing to the overall global model and how well it's performing. But usually with explanations regarding automated decision making, what we really care about is the local interpretability. That is, how important was my blood pressure or my glucose level to this decision that you made about whether or not I have diabetes? And so try to highlight this importance by the coloration here. You can see, for example, the first patient, for example, the glucose is the biggest driver and the blood pressure doesn't really matter at all, whereas the second patient, both the glucose and the blood pressure are probably contributing equally, and age doesn't seem to be as much of a factor, for instance. So we need interpretability methods to be able to produce explanations, and there's also different classes of these methods. One of them is considered anti-hoc interpretability. So the idea here is that we train a simple model, so one of these models that we understand, like linear regression or decision trees, and then we're done, basically. We know that the model is intrinsically interpretable. Because it's simple, we can explain it very easily. But there's some shortcomings of intrinsic interpretability. One is it typically requires a model-specific explanation. So in order to explain a linear regression model or a decision tree, it requires some rudimentary understanding of how the model works. And every one of these explanations now can take a different form in this explanation. So you can't give a decision tree back as a visualization, as an explanation for a linear regression model. It's just not possible. So it's dependent on the type of model that you're using. They can also be immediately undermined by feature complexity. So if you're using uninterpretable features, it doesn't matter how intuitive your model is, the features aren't intuitive, so you can't really return anything that's easily explainable. So for example, if you're performing a principal component analysis ahead of time, and then you feed that into a linear regression model, even if that linear regression model only has 3 features that matter, if no one understands what those principal components are, you're out of luck. And then finally, we already showed, I'm just going to jump back. We're already making a sacrifice here for performance by going with these anti-hoc interpretability methods. So simplicity requires sacrificing performance by its very nature. And being able to fully comprehend a model is fairly limited in what a human can do. So anything, once you get above 3 dimensions even, it's becoming pretty iffy if you can really actually understand that all at once, which is what usually people consider from something that is intrinsically interpretable. So what's a better path? What people are now, there's an area of active research and what's becoming more in vogue are post-hoc interpretability methods. So the idea here is stick with your neural network, which we know has good performance. So now we're training a complex model, and then use a separate method, perhaps one of these inherently interpretable methods, to be able to interpret it further. And so a lot of these methods are considered model-agnostic explanations. So if you just consider like very simple machine learning pipeline of you take your data to build some black box model and it's not interpretable by the human end user, we're just adding on an additional step to this process. We're basically opening up the black box with some sort of interpretability method so it's more consumable by a human. A major advantage of this is that it allows us flexibility in the models that we use. So it doesn't matter which model we use, we can evaluate the models the same way, and this allows us to do comparisons between different models as well, which is not something we really had with these intrinsic methods. And most of these model-agnostic methods rely on basically perturbation methods. So if you imagine you have an array of features that go into some sort of black box model here, and you get some sort of output, how these models work is you're just sort of varying one feature at a time. So for example, this color variable, and seeing what is the impact of that on the output, essentially. And so most of these methods work with this general framework in mind in order to sort of reverse engineer what input of the data is leading to the various outputs that you get. So the most popular, perhaps, at least open source method is known as Lime. So Lime has all the flavors that we've talked about that make a good interpretable model. It's local, it's interpretable, of course, and it's model agnostic. So how this basically works is what you do is you select an instance that you're seeking an explanation for. So on the right here, that's visualized by this big bright red arrow. And what you do is you just perturb your data set and generate a bunch of predictions. So all these other points are just basically perturbations of your original data point. And then you weight them by how close they are in proximity to your original data point. And that's indicated by the size here of the various points. So you see, like, whether it's a blue circle or a red cross, the larger it is, the more it's weighted. And then you fit just a weighted interpretable model. And so this allows you to generate a local explanation by using this interpretable model. Very often, like a lasso regularization is used, but you're really able to use any interpretable model if you so choose to do so. And this generates, what's important here is this is a local explanation of the model. So this isn't something that will apply globally to understand every single point or every single prediction in your data set, but it will be at least one way to provide an explanation for that single point. In BigML, we have a similar method that's also local and model agnostic. Our perturbation method is a little bit different than what was written in Lime. So we don't call it Lime, we just call it prediction explanations. But essentially, if we just use this original diabetes example again, if we were to input some data about a patient, their BMI, for example, plasma glucose, or age, you'll get the probability of that patient having diabetes or not, and then you can also choose to return some sort of importance to how important was that individual variable's value into making this decision. And so while global feature importance would be the same for every single prediction, every single patient, if you have different patients, for example, how much plasma glucose weighs in making this decision can vary, for example, between different individuals. Lime's also really good for dealing with different types of data and model agnostic methods in general. So we talk a lot about tabular data mostly, but there's also ways to be able to do the same thing with image data, for example. Here your perturbations are typically what are considered superpixels. So rather than just varying a single pixel, there's some sort of segmentation method applied first to find like an area of pixels that all tend to be the same color to segment the image, and then you vary that pixel one at a time to see like what is the impact or what's really explaining this prediction. So this is from the original Lime paper, and you can see you get an explanation for what part of this image isn't explaining an electrical guitar, which of them are explaining an acoustic guitar, which are very, very similar things ultimately, but you can see the distinction there. It's picking out the wood versus the neck of the guitar. It can be applied to text data just as easily. So this is an example where the mission was to identify words in a data set where everything was labeled a disaster, but some things were real disasters, and some things were sort of like metaphorical disasters, like this talk was a disaster or something like that. And so you have, you can highlight the words that are most important here. And again, this gives you a short list of words which are most important only for the example that you're providing it. So there's a very short sentence as the input here about the atomic bomb in Hiroshima. You can see how words like history and one were not relevant, and words like murder and mass and so forth were relevant for making this decision. Okay, so I'm going to conclude with some final thoughts regarding machine learning interpretability, especially in the GDPR era. I think the most important thing is to remember that humans are ultimately the end consumer when you're talking about machine learning interpretability. There was a workshop at NIPS last year on the same general area, and if you read all the titles of the talks, like, I couldn't understand half of them, what they really were referring to. That's not really what the goal of interpretability is for machine learning. It's not to make things as complicated as possible. It's to be consumable as well. So to really remember the spirit of the law. Model-agnostic methods seem like they're going to be advantageous going forward, and I'm sure more will develop over time. This adds just an additional layer of abstraction, and it's very nice from an engineering perspective as well because of that. They can also provide a very nice exploratory system that you can allow an individual to interact with and really explore how their decision could be tweaked if they change something. But finally, reading some law logs about this, no one really has a grip on what it means in practice. And that's a direct quote from a legal expert on this. We're still in the early days in the GDPR era, and I think ultimately time will tell how this gets processed by regulators. But for now, I think better to stay safe than sorry and apply these principles as much as you can. So that's all for me. Thank you.